Okay, so let's start to talk about the time complexity. In this course, when we are talking about the time complexity, the goal is we care about the asymptotic performance. And the answer or the goal when we are when we are talking about the time complexity or the big O is, we are worrying that if we have a algorithm and then we plug in a really large data. Okay, if you have a sorting algorithm, it doesn't matter it is some fancy sorting algorithm or it is a really basic bubble sort. If you only have 100 or 1000 of the data and then you plug in, you get it sorted, you don't worry about the time complexity because our computers are fast enough. However, if you have 1 million of the data and then you will start to worry about the time complexity. And for this part, we are talking about the running time. And other than the running time, we can also use the similar algorithm analysis to evaluate the resources that an algorithm may consume. And for the resource, it could be our time, it could be the memory or storage, it could be some other thing like even the power you have to use to run this algorithm. Okay, and for the asymptotic notation, and usually we are using the big O. In this course, today, and then the next course next week, and we are going to talk about what does a big O mean? And what's the difference between a big O and big O n square or big O n log n? What are the difference? Which one is good? Which one is okay-ish? Which one is not so good? Okay, and then if you're using this kind of notation for the running time, can we also use that for the memory consumption, for example? Okay, so we are gonna do some hypotheses before we move on. Number one, we want to talk about the computer architecture. As you may know, there is a cool thing called Qualcomm computing. If we are using Qualcomm computing, and then probably all the time complexities, all the worries about the running time won't exist. Okay, so in this course, we are still talking about the traditional old-style computing architecture. We are using random access machine. And then we are assuming that all the memory pieces are equally expensive. And then we are assuming that all the data types are of the same length. For example, you may know for integer, they are smaller than float numbers. But in this course, we are just assuming that all the data types, they are of the same length. Okay, and for when we are talking about the time complexity, that time complexity is related to the input size. And for the input size, if we are following our discussion about the sorting, and then the input size is how many values we are trying to sort. Are we trying to sort 100 value or 1 million values? And that is the input size. And of course, as you may feel, for a lot of the algorithms, the performance or how long it will take depends on the input size. If you have a very small data set and probably don't have to worry about the running time, it doesn't matter if it is a really basic one or it is a fancy algorithm. But if we have a huge data set and then we want to make sure that our algorithm is optimized enough, okay? And then for different type of the algorithms, and then for the input size, they may also mean different things. And for example, if we are talking about graph algorithms, and in a graph, there are two different size of the data. Number one, how many nodes do we have? And number two, how many edges do we have? Okay, at the very end of this course, and we are going to talk about some of the graph algorithms. And for now, you only need to know for the input size, it could mean one thing, which is the number of the value to be sorted, or it could mean multiple things like the number of the edge plus the number of the nodes. Okay, so well for the running time, running time should be a polynomial of the input. Well, and before we talk more about the polynomials, I want to remind you when we are trying to figure out the time complexity, we are counting, or we are trying to get the number of the primitive steps executed. And well, coming back to our assumption here, we are assuming that all the primitive steps are equally expensive. So they are requiring almost the same time to run any type of the primitive steps. So well, and then the time complexity, or how long an algorithm is going to run related to the input size, will become how many primitive steps is required so that we can finish this algorithm on a given size of the input. And that will be the polynomial we are trying to figure out. Okay, so and then for the analysis, well, usually we don't worry too much about the best case. And for example, if you're doing sorting, what's the best case? The best case is, say, you have all the values pre-sorted, and then for a lot of the algorithms, well, there's nothing to be done. But we are not discussing the best cases. Even we are discussing the algorithms, we are either discussing the worst case or the average case. So for the worst case, what is the worst case for a sorting algorithm? So is that all the values are sorted in the reverse order. Say we have a sorting algorithm, we want to sort the values from low to high. And for the input side, we have a pre-sorted list from high to low, and then it seems that there's a lot of work to be done, right? But depending on different algorithms, and that might be the worst case, or it may be not. Okay, and then how about the average case? How do we really define average case? Well, and if we are talking about sorting algorithm again, and probably the sorting algorithm should be, for the sorting algorithm, a really average one should be all the values are just random. They're not pre-sorted low to high or high to low. We just shuffle the cards, and then I give all the values to the machine and say, okay, sort all the values. Okay, well, this might be a reasonable average case for a lot of the algorithms. Okay, so next we want to talk about another sorting algorithm. And by the way, if you have already coded the bubble sort, and probably you will have some idea on how the bubble sort can be done. Well, the long story short, for the bubble sort, well, in each round, what do we do? Correct. So we are comparing one pair of value, and then if they are not in the right order, we swap, and then we move on to the next pair, and if it's necessary, we swap again. So we have one pair of the value and move down from the from beginning to the end. And after one pass of the bubble sort, what have we done? That is, we at least put one value into the right place. Right? So that's the bubble sort. So in the bubble sort, well, for a lot of swaps, they're not necessary, but after a full pass, well, for the full pass, I mean one round of the outer loop. And then what have we done? We have at least put one value into the right place. Okay, so today we want to talk about another sorting algorithm, that is the insertion sort. And for the insertion sort, well, the concept is really easy. And then if we are drawing the card from a deck, and then you put you put the cards into your hands, and then how do you do the sorting? Say, well, I draw the first value, which is 5. So this is the only card I have, which is 5. So I'm holding that. And then say I draw 3. Okay. There's 3. So 3 should go lower. So I have 3 on the left side. And then I draw another card. I draw a 6. And then 6 is greater than 5, so 6 goes here. And eventually I draw 1, so 1 is even lower than 3, so 1 goes here, right? Oops, I don't have big hands. Okay, but this is how we do the sorting. So what's the idea behind the insertion sort? In the insertion sort, we are using one hand to hold what? To hold a sorted portion. So it doesn't matter what value do we have. Say we have 1 and we have 6. Okay, 6 goes here. And then we have 5. 5 goes between 1 and 6. So it doesn't matter the sequence. But we are using one hand to hold the sorted portion. That is the thinking of the insertion sort. We are always trying to control a sorted portion. And then for a new value to come, we want to insert that into the right location, and that is the sorting algorithm. Okay, so well, for the sorting algorithm, sorting cars using two hands, that's easy. But for the sorting on a list in place, and this is how it can be done. So we are starting from the I from 2. So why do we want to start 1? Because for 1, we are assuming that we only have one value, and for that one value, there's nothing to be sorted because we only have one value. That one value is already sorted in the right place. And then we are what? We are expanding the sorted portion. So we started from only one value. That one value is sorted, and then we set the I to be true. So for the I as 2, our goal is we want to have the first two values be sorted. Okay? So, and how do we do that? We are assigning the AI, well, at the beginning I will be 2, and then the A2, we put that to the key. So the key is the value we are trying to look the right location for. Okay? And then our goal from line 3 to line 8, our only goal is we want to find a right location for the key, and the key holds the value for the AI. And how do we do that? We are going to assign I minus 1 to the j, and then as long as j is greater than 0 and aj is still greater than the key, what do? We want to shift the aj to the left side or to the right side. So we are moving the higher values than the key, the values higher than the key to the right side, and then eventually we want to stop at the place, and that is a place for the key. And what is the key's value? The key's value is AI. So every round, we are trying to expand the sorted portion. So, well, I started from 2 because when we only have one value, that value by itself, it is sorted. Okay? Well, this is not a very intuitive explanation of the insertion sort, but I'm going to stop the video here, and the next video I'm going to walk you through the insertion sort using an example. So I will see you in the next video.